Okay, so I've been asked by a student to help work out some problems in Chapter 16 and Chapter 17, even though we haven't really gone to Chapter 17 just yet. But I'll go ahead and walk through some of these guys with the hope that, by looking at some of these, we will better understand how we approach this, and you can use this so we can be better prepared for class. So, step one, the problem one we look at on Chapter 16 was problem number 6. Problem number 6, question view. They want us to find what is the of solution, what is the different concentrations of the solution A and B if we're given OH minus or H3O plus, and saying which one are basic or not. So this is relatively easy once you get the gist of this. This comes down to our KW expression. KW equals 10 to the negative 14th, which equals H plus times OH minus. So, that in mind, if we know H plus, we can know OH minus. If we know OH minus, we can know H plus or H3O plus, because they're all related there. So as the concentration of base goes up, the concentration of acid would go down. So for solution A, say 10 to the negative 14th, we divide this by our concentration of OH. Please note this is capital E, which means times 10, whatever. You want to make sure that this is, you're doing the right division, you're doing the right solving of this so that you're not multiplying the 10 to the negative 14th by 10 to the negative 7th, but you're dividing the 10 to the 14th by 10 to the negative 7th. If you do not get the following answer, you have not done it right. So I'm going to do this real quick. You should get the concentration of H plus is equal to 2 times 10 to the negative 8th. 7.2 times 10 to the negative 8th. If you did not get that number, make sure your order of operations are correct. Make sure you're including the right parentheses. Find some way to make this a little bit easier to type this in. The same thing for number 2 over solution B. We're going to say, well, 10 to the negative 14th. Divide by 9.51 times 10 to the negative 9th. Same thing. 9.51 e negative 9. You should get the amount of base is 1.05 times 10 to the negative 6. And I'm not going to bother to do C, but the same premise. You take 10 to the negative 14th, our KW, and we divide by our H plus to get our OH minus. The final part of this question is this the solution's acidic or basic? Well, to be basic, you would have to have greater than 10 to the negative 7th concentration of OH. So if the amount of OH is greater than 10 to the negative 7th, then it is basic. So I'll just give you this one. A is indeed basic. It's 1.39 times 10 to the negative 7th is greater than 1.0 times 10 to the negative 7th. So based on your answers, you should know what is B. And just thinking about that, you will quickly find out, is C basic or not? You should be able to do that. Select all, I'm going to delete these so that it's clear. Okay, that is number 6. Let me make sure this is. Just want to make sure. Next one, number 8. Question for you. Number 8 asks, number 8 asks us, find the OH minus, the pH, and the POH following solutions. Or find the H plus pH and POH of this base. So we have 2 relationships. They're all related. Let's see. H plus times OH minus equals KW. We have negative log of H plus gives us pH. We have negative log of OH minus gives us POH. And we have pH plus POH equals 14. And there's actually one more relationship. But those are the main ones. We can also say that H plus equals 10 to the power of negative pH. These relationships are gone over in depth in a little video I just uploaded with the help of Hunter, where we just I went a review of all of these things. So if you need further review of this, check that video, the supplemental lecture notes. In the meantime, so let's look at this. We have concentration of H plus. So say, what is the OH minus? We're going to say 10 to negative 14th. We're going to divide KW by our H plus, and that will give us our OH minus. Since this is a really small number, the that means the result will be a bigger number. So find that, we get 1.49 E negative 6. Hopefully you'll agree that 1.49 E negative 6 is a bigger number than 6.7 E negative 9. Now to get the pH, you're just going to take the negative log of our 6.7, our negative log of our H plus. Negative 9. We do that. Negative log 6.7 9 will give you 8.17. Now if I take the negative log of our OH minus, you will get your POH. Get 5.82 or 5.83. Now please note, if I add 5.83 to 5.83 to 8.17, they should add up to 14. And indeed they do, because of those magic relationships I just talked about. So you would do the exact same thing for the second part. The second part is just, you would start with OH minus, and so you find H plus. Then you'd use that OH minus value to find POH. You find that H plus value to find pH. So you're just repeating those same steps, except with OH. So this is not hard, it's repetitive. You just need to think about what you have and thus what you will get. So number 9. This one is harder than any of the other values because of one little factor. And this is something that I also mentioned in the video, supplemental video. Barium hydroxide is a dihydroxo. So yay, OH2 means when this dissociates, it produces 2 moles of OH. 1 mole of barium hydroxide produces 2 moles of OH. So if I have 0.00056 molar barium hydroxide, I'm going to have to multiply by 2 to calculate my OH minus. So 0.00056 times 2 is going to get double the quantity, 0.112 molar. Now with that in mind, Kw is 10 to the negative 14th still. And so H plus is just going to be Kw divided by your OH minus. If you could do that in problem number 6 and problem number 8, you should be able to do this in problem number 9. So, I said this is not that's a little bit harder because it's a dihydroxo, but it should not be fatal. Let's see, that's number 9. Number 11, pH. Okay, this one is, it's not necessarily hard, it's just more of a review than what maybe we're used to. A solution of sodium hydroxide contains 5 grams of sodium hydroxide per 100 mils of solution. Calculate the pH and the POH. So, what you have to do is you have to remember your molarity. How do we calculate molarity? Well, we would turn, molarity is defined as moles over volume. And moles are defined as grams over molar weight, or molecular weight. So if I have 5 grams and the molar mass of sodium hydroxide is 40 grams per mole, how the hell did he know that? Yeah, I'm a freak. Gotcha. 17 from oxygen and hydrogen plus 23 from sodium, that's 40. I've used it quite a bit. So you can find our moles. Pretty straightforward. 5 divided by 40. It's like 0.125 moles. Our molarity is thus 0.125 divided by liters, so 0.100 liters. With that in mind, your molarity would be 1.25 molar base. So from that, you can calculate your POH. So you take your negative log of that and you'll get your POH. Don't worry about the actual number. Write down your negative log of that. That's your POH. Now to get your pH, you're going to subtract 14 minus whatever your pOH is. Don't worry that this has blown the scale completely away. That is possible. The pH scale is only that. It is only a scale used to deal with this. It's possible to have a negative number. It is possible to have a number greater than 14. The scale is only that, a scale. If it goes past the scale, it just means it's really strong. Don't fuck around. Now, I'm going to go ahead and look at these two. There's two pools. Pool questions. So you could get one of two options. We can look at both of them. I really don't care. We'll go ahead and do this. Select all. So HClO, what Na? Okay, Na. Well, HClO is a weak acid with a Ka. NaClO is a weak base. What is the pH of a solution that is 0.080 NaClO? So this one I also kind of went over in this supplemental video. Our idea here is we have a basic solution. If NaClO is a weak base, you have this reaction happening. You have ClO minus plus water goes to HClO and OH minus. I ran out of room. Whatever. So your expression for this would be Kb equals HClO times OH minus all over ClO. But you're like, Andrew, we don't know the Kb. But you do. You just don't know that you know. Because we know 10 to the negative 14th, or Kw is equal to Ka times Kb. So the fact you're given Ka, you can calculate Kb. So you say 10 to the negative 14th divided by my Ka 4.0 times 10 to the negative 8th. So 1 e 4 e negative 8. You get that. You get a Kb that is 2.5 times 10 to the negative 7th. 10 to the negative 7th. So we have a Kb. We have the concentration of our ClO. That is equal to 0.08. Now, all we have to do is find our OH minus concentration. So I'm going to go ahead and clear this. Hopefully, you've done the ICE table enough. You've seen the trend that almost all of these guys will break down into this. Kb equals x squared over our base, where x is equal to OH minus concentration. So our Kb, which was, we determined 2.5 times 10 to the negative 7th. Our base, which was 0.08. All that equals x squared. So all that equals x squared. So we multiply those two numbers together to get 2 times 10 to the negative 8th equals x squared. We have square root both sides. to get our x. So I get my x is 1.41 times 10 to the negative fourth. So because this is OH minus concentration, we take the negative log to get our POH. So remember, because this is OH minus, it gives us POH of 3.85. pH is 3.85, and then we are not done there. Because they have asked us, like I will often ask you, what is the pH? What is the pH of that? You have to take 14 minus 3.85 to determine the pH. And that will give you your answer. Now, this problem, the other one you could get is ammonium chloride. As you do that one, it is everything we just did except in reverse. Because they give us a weak base, and then they say, what would the pH be if I had the conjugate acid? The only difference here, if you get the ammonium chloride one, is you do not have to turn your pH into POH. You stop at this step right here, because we'll be looking for a Ka expression. A Ka expression will give us the H plus. The negative log of H plus will give us our pH. So with that in mind, that one is actually a little bit easier, but not much, just a smidgen easier. So don't go thinking, oh, I'm going to have I got the hardest version. It's like, no, it's not bad. So those are those problems on chapter 16. I'm going to go ahead and look at the chapter 17 problems that someone has asked for. Because people are starting to work ahead, even though, hey, oh no, we're not quite there yet. We'll hopefully get into this chapter next class. So looking at problem number 3, buffer. Buffer. So buffer is essentially what happens when you have both weak acid and conjugate base in solution. That our Kb expression, typically when we had our Kb expression, your Ka or Kb was equal to the H plus times A minus over HA. And because we had 0 concentration of A minus, we set those as X and X squared over HA. But now we have an unknown amount of H plus and a known amount of A minus. So we're going to actually separate those out. And so, with that in mind, we have what's called the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation rearranges this so that I take the negative log that pH equals the pKa plus log of, what's like, I'm trying to think. A log of what, like A minus over HA. I'm not mistaken, right? It's over 2. Times 0.45. Okay. Okay. I just want to double check. So the other version of this, so the Henderson-Hasselbalch is that pH equals pKa plus log of A minus over HA. The other version of that would just be the flipping it around for the basic condition. So flipping around for the basic condition just basically gets us POH equals pKb plus log of base on top on bottom, conjugate acid on top, or otherwise known as log of A minus over HA. Acid on top, base on bottom, and that'll give us POH. So the fact this buffer, they give us the concentration of base, they give us the concentration of conjugate acid, and they give us the Kb. That is all we need to solve for this equation. So now the question is, what is a pKb? pKb is the same as pH or POH. When we took the pH, we took the negative log of H plus. When we find the POH, we took the negative log of OH minus. So a pKb is the negative log of your Kb. So the negative log of this Kb, negative log of Kb, would give us our pKb. And as we'll see in class in the next couple days, a buffer is only good within plus or minus 1 unit within the pKb. So their starting number is 4.33. That's our pKb. That's a negative log of our Kb. Now, we're going to add on 4.33 plus log of our acid over our base. So because we have more acid than base, this is going to make this slightly more acidic. So we add on log of 0.45 over 0.29, and you get 4.52. So your POH is 4.52. Once again, you need to carefully watch. What are they asking for? They are not asking for POH, they're asking for pH. So from there, we need to flip that around. So 14 minus 4.52 would be your pH. So this buffer is 9.48. Other than that, that's not particularly hard. Let's see. Just want to make sure. Okay. Ooh, okay. I may end up throwing some of these out. I may leave the problems in. Shoot, one thing. Ah, crap. I will go, right now, I'm going to leave them in for now. But we are not going to cover these nearly as heavily as we would otherwise. So they ask you, calculate the initial pH before any titration is added. Oh. Calculate pH before any titration is added. So how do you do this? How do you do this? This is literally number 4. Good Lord. Okay. Okay. If you have a base, this one's pretty easy. This is a strong base, so the pH before any titrant is added, so then take the negative log of this concentration. The negative log of that concentration is going to be, all of it's going to dissociate. Well, actually, sorry. 25 ml sample of KOH is titrated with 0.75. So before any acid is added, we just have 0.35 molar base. So 0.35 molar base, the negative log of that is going to be our POH. And then from there, we need to just simply find the pH. There's going to be a POH, like negative log. So it's going to be pretty small, so 0.46. And then we subtract that from 14, so 13.54. Not bad. Now, what is the pH after 5 mils have been added? Okay, so this is a little bit harder. Okay, so for this, you need to do what's called a subtractive ice table. So what we have to do is calculate the moles of acid and the moles of base after that point and subtract out until one of them is gone. So I'm going to create an ice table real quick. We have to calculate the moles and then the new concentration. So OH minus. Let's see. OH minus H plus. OH minus, we have 0.35 molar and we have 25 mils. So the moles of OH minus is 8.75. Now we have 0.75 molar acid and 5 mils of that. So it's 3.75. So in this titration, we're going to neutralize acid with base until one of them runs out. So after 5 mils, we have 5 moles of base left. But before we can calculate pH or POH, we have to divide by our volume. So we added 5 mils. So when we added 5 mils, the volume changed from 25 to 30. So 5 divided by 30, what's the concentration of base that's left? Concentration has gone from 0.35 to 0.167. So we take the negative log of that, and that will give us our POH. POH of 0.77. And then we flip that to give us our pH. That's a kind of tricky one. As I said, I'm not sure how much I'm going to focus on some of these guys. I might throw some of them out. Oh, jumping straight to number 12 and number 15. Equilibrium constant. Oh, okay. As I said, some of this was considered before we lost a week of class. So some of this I'm going way. There's going to be a couple classes in the future. So the new concept that we're going to cover as well is KSP. It is the solubility constant. The reaction we're going to see is silver, or like how does something dissolve? We have silver sulfite breaks down reversibly to 2 silver positive and 1 sulfite negative. 2 minus. Now, because silver sulfite is a solid, silver sulfate is a solid, it is not included in the K expression. So KSP is equal to products raised to the power of their coefficients. So silver plus squared and sulfite to the first over 1. So we don't consider the reactants at all. Now, with that in mind, if you know the KSP, which you can find on that table, and you know the concentration of silver, you can find the concentration of sulfite. The KSP, I'm going to click on there and look at this table real quick. KSP for silver sulfate, silver, another S, so silver sulfite is 1.5 times 10 to the negative 14th. 1.5 times 10 to the negative 14th. Meaning, if I have 3.3 times 10 to the negative third, plus 3.3 times 10 to the negative third squared silver, how much sulfite must I have? So I'm going to take my KSP divided by my amounts of silver, and that will result in the amount of sulfite that must be found in solution. And it's a really small number, but that is okay. It's okay. The last one I've been asked to look at, let's see, is number 15. Once again, we're getting way, way, way beyond what we're covering right now. So number 15, calculate solubility. Okay, one of 2 or 3 problems. Okay, what is the KSP of this? So if our salt has a generic molar mass of 299 grams per mole and has a solubility of 6.7 grams per liter, what is the KSP? Okay, this one's actually, they're not actually too bad as long as you understand the concept of KSP. So looking back at this guy. Well, I think I just got a whole new numbers, but that's okay. It's not a big deal. It's not a problem. The idea here is you want to find out what concentration dissolves. What concentration dissolves. So if I have 3.9 grams in a liter, and I have 177 grams in a mole, I want to know how many moles in a liter. So I'm going to take my 3.9 and divide it by my 177. That will give me moles in a liter. 3.9 divided by 177. So in that particular problem, I would have a concentration of 0.022 moles per liter. Now, with that in mind, that is the concentration of both A and B. Both A and B. So KSP for this guy would have to be 0.022 squared. Or the KSP would have to be 4.85 5 times 10 to the negative fourth. Now, in a problem like this, I'll go ahead and do this one because this one's one step harder. One step harder. So with this guy, same process. We have to find out what is my molarity. 2.2 divided by 199 gives my molarity. 2 divided by 199, and that gives how much AB squared, AB2 dissolves, and that's 0.011. The problem is that's 0.011A would dissolve, but every A that dissolves would produce 2 B's. So A concentration is 0.011. B would have to be double that, 0.022. And so the KSP, which is going to be, KSP is going to be equal to A times B squared. So 0.011 times 0.022 squared. So you get something like 5.35 times 10 to the negative 6. Okay. Now that's a lot of problems, a lot to work with. Some of these we may not cover very much in class because I have to cut out some of it in order to save time and make up time in class. But hopefully this practice will help you as you work through the homework and help you understand some of this. So have a good day, and I'll talk with you tomorrow.